Hello and welcome to section 4.5 integration by substitution. In this video I'm going to give you just the start of how we integrate by substitution, and so and then in class we will do a lot more to make sure that we all feel good about this. So we are going to integrate this, and you can see that you do have an option. You could multiply this all out and then integrate it that way. But what we can do is, this is kind of the reverse of the chain rule when we do this, and so what we're looking for is we're trying to recognize a pattern that there's a function inside of a function multiplied by the derivative. And you'll notice that if I was to say that this was my inside function, that if I said that g of x is equal to x squared plus 1, then I could say, well, then this function would turn into g of x squared. And actually, let's change this. We're going to actually do this as a u substitution instead of g of x. I like that a little bit better. So we're going to say our function in here is u, and so they're going to say it's x squared plus 1. Well, if I differentiate that, then I would end up with 2x dx. So you'll notice that this 2x dx right here matches up with du, and I could then replace the x squared plus 1 with u, and now I have a function that is all in terms of u. So I could rewrite my integral, and this is the substitution I'm talking about, is that u squared du. And so now I can integrate the inside this function much easier. And so when I integrate that function, well, I add a power to it and divide by the new power. So I end up with u cubed divided by 3 plus c. And then if I go back and plug in x squared plus 1 for u, I end up with my final function as 1/3 of x squared plus 1 cubed plus some constant. Now, this may or may not make sense at this point in time, but let's go ahead and just differentiate it just to make sure. So we're saying that this is actually y equals 1/3 of x squared plus 1 cubed plus c. Now, if I was to differentiate it, I should end up with what I started with. So let's go y prime. And so differentiating this takes a chain rule. So I multiply 1/3 times 3. And I reduce the power by 1, so there's my square, and then I differentiate the inside, which will give me 2x, and the c is a constant, so that goes to 0, and with a little bit of cleanup, y prime becomes x squared plus 1 squared times 2x. And that's dy over dx, so I could put the dx on the other side, and therefore I end up with the same thing that I had before. And so, using my differentials, it could be written as dy equals x squared plus 1 squared 2x dx. And so that is what I was looking for. So my check, this is the final answer that I needed for the integration. But checking, that gave me the same thing I started with, so we're all good. That's what we're doing. So then in example 2, we're going to do a trig function, and in this one we're looking for a pattern. And so my inside function, my u value in this case, we'll say is 5x, which is a little bit different than what we were used to before. If I differentiate 5x, I get 5 dx. If I differentiate my u, I get 5 dx. So then that would be this 5 here, and the dx taken care of. So now really I could rewrite this as the integration of cosine of u du. So now I don't have an inside function to deal with, and so if I integrate cosine of u, well, to get cosine, I had to start with sine, and so this becomes sine of u. So my y turns into sine of u plus c, and so then if I replace u with 5x, y, my original function, is sine of 5x plus c. So again, we could check this and take the differentiate this. So y will equal sine of 5x plus c, and so then dy would be, well, differentiating the outside would give me cosine of 5x, and then differentiating the inside, which is 5x, is times 5. Remember, a constant goes to 0, and since we're dealing with differentials, I'm going to put my dx over there. And so I get 5 cosine 5x dx, which matches what we started with. So this, I did my anti-differentiation correctly. All right, and then there's other things that you could do. We have this constant here that we were multiplying by that, well, we'll just kind of go through. This is a little bit different, but same idea. So in this case, if I'm going to integrate, well, I'm going to take my inside function, and so that's going to be u is going to equal x squared plus 1. Du, when I differentiate, is 2x dx. I have a little bit of a problem here. I've got my dx, and I've got an x, but I don't have the 2 there that I need. So I have to turn this 2x dx into the same thing. So what I'm going to do is I'm going to divide by 2 on both sides, so I get 1/2 of du equals x dx. Now that looks just like what I see over there. So now I can replace my x dx with 1/2 du, and I can replace my x squared plus 1 with u. So I'm going to integrate this and say, well, my u, I have u squared, and it's times 1/2 du. Well, this 1/2 is a constant multiple, so I can move that out front. And so then I really have u squared du. And now if I integrate u, with respect to u, I'm going to get 1/2 times u cubed divided by 3, and then add on my constant. And it doesn't matter if my constant was inside the parentheses, half of a constant is still a constant, so I'm just going to leave it out. And so then I end up with u cubed over 6 plus c. But my u, remember, from up there, is the x squared plus 1, so I end up with 1/6 of x squared plus 1 cubed plus c. So that is my final function, and if I was to differentiate that function, just as a check, then I should be able to get back to what I started with. And so, oops, I didn't need the prime there yet. So I will differentiate y, and then if I multiply by 3, well, if I do my power rule, I get 1/6 times 3, and following my chain rule, I'll differentiate the inside, which is 2x plus c. Well, the differentiation of the constant, remember, is 0, so I don't need that. And so then dy, and there's a dx over here, because that's what I differentiated with respect to. 2x times 3 is 6x, and then times 1/6 will just get me x, and then I'm left with x squared plus 1 squared, and that is what I started with. So again, I'm happy about that, and this was my final answer. So we will talk more and practice a little bit more of this stuff in class. So if you have any questions, please come to class prepared to ask them, and like I said, we'll do more of this.